Hello and welcome back to Calculus 3. This is section 12.4 on partial derivatives. So, we know about derivatives from Calc 1, and those derivatives are done along x-axis. So, when you have the two-dimensional realm, which we call R2, we draw the xy plane with x being independent variable and y being dependent variable, and we have some function f of x in there. We understand that there is a tangent line at point A, which measures the instantaneous change at that point. Now observe that if I am to rotate this system 90 degrees around the y-axis, everything that I see there would just look like this, right? Because that's technically the thickness of it. It's just a straight line. Everything is on a pile. Where x-axis would be pushing out of the screen right there, and this would be your y-axis. So we see that the derivative of this function f of x was along x-axis. Now when we move to Calc 3, so we move to R3, we have the two-dimensional domain. So now, if I have some kind of surface on the xy if I have some kind of surface on the xy, now this is a three-dimensional thing, then I can take the derivative in respect to x. And as I am taking the derivative in respect to x, that is going to give me some kind of path which will be there because I am technically cutting this shape along the x-axis, and this red line would actually represent my Calculus 1, right, 2D case, and then I am taking the derivative. So now I can draw the tangent line, let's say here, and the slope of this tangent line would be what we call partial derivative of z in respect to x. So now we have a new symbol for derivative. It looks like this, right? This is the partial derivative, this, right, or y, whatever you make, but that has to be the symbol. Now, obviously, you might run into trouble if you write number 2 this way. So please be careful not to confuse things, okay? I write my 2's this way, so I'm good, all right? This is supposed to be, right, lowercase d with a little hook going this way, so partial derivative. Keep practicing the symbol. What happened? All right. So now we have another one, which would be my partial derivative in respect to y, because I can cut this shape in the y direction as well. So if I cut the shape in y, oops, this needs to be blue now. So if I cut along the y-axis, I'm going to have some path on y and then not see the other side going down to the y-axis. I can pick a point somewhere where I'm going to have a tangent line whose slope is going to be partial z partial y. So the partial derivatives we are learning today are only in the direction of x-axis and the direction of y-axis. Next week we are going to learn directional derivatives, and those will be in any direction, because we will have a vector to give us the direction in which we want to find the derivative, and we'll deal with that later. But currently, the only two directions that you are taking derivative in are the red and the blue, which is x and y axis cuts. Yes? What happened? Yeah, slope m. Slope m of the tangent line is equal to the derivative. Now, if you are looking for, and again, honors, pay attention, right? You need to know this derivation. It's the same like in Calc 1. If you're looking for the definition of the derivative, we have the same derivation with the good old limit of f of x plus h minus f of x, right? Except now you have two variables. So you just have to keep putting comma h. Comma y on everything. So the definition, I want to do the red one. So what is the definition of the partial derivative in respect to x, which is known as this, let's put df dx. So this one is going to be the limit and then we have now f of x plus h comma y minus f of x comma y divided by h. So this is our standard, h goes to 0. And then we have our blue one, which is fy, partial f partial y, is limit h goes to 0 of f of x comma y plus h minus f of xy divided by h. The derivation for this is done in a textbook. So the honors, obviously you need to know the proof. That could be the question on the next exam. And it's identical to Calculus 1 proof. So if you know, I know that most of you took honors Calc 1, so you know that your Calc 1, if you know your Calc 1 proof for derivative of x, this one you just need to put every f of x plus h comma y. So you just need to add comma y to that proof, and it's the same. Now, we know, because we took Calc 1, that we don't have to work with these limits from definition to come up with the derivatives of our function. We know that there are shortcuts which we memorize, like derivative of sine is cosine, derivative of e to the x is e to the x. So we memorize those so that we don't have to go through the annoyance of limit to compute derivatives. Well, now we are going to do the same thing. We are going to learn how to take the partial derivatives of these functions without actually working the limit. And that's something that we need to practice a little bit. So our new functions are z equals f of xy. This is what we've been studying since the beginning of chapter 12. And we know it gives us some kind of surface, like an umbrella or wavy thing, whatever, right? And we know we have a domain underneath, and we have domain is xy plane, and z is just a z value where the height of each of those points is. So what do we actually have? Well, if my independent variables are x and a y, then my partial derivative in respect to x, and this is the notation for it, you put f and the small x in the index, it will be partial f, partial x. And fy is partial f, partial y. This notation tells me that I am cutting my shape along x-axis, and I am taking the derivative of whatever line is there. I think they do have a very nice picture in textbook, so which shows the shape and then the cut and then the outline. So take a look at this is page 896. You have the entire shape, which is this orange thingy. It's like a pile of sand. Actually, no, don't use a pile of sand. You can't cut that. You cut the pile of sand and distribute it. So, I don't know, dough for cookies or whatever it is, right? And you see the plane, which is going to cut as the x-axis, right? So all of the cuts are done in the x-axis direction. Now, the plane of the cut and the surface of the shape will create this two-dimensional line, right? Two-dimensional black line over here, which is the line of intersection. And that line has a point at which you are computing your partial derivative, and that's the tangent line. So partial derivative. So you can measure the slope of that line by computing the partial derivative. So that's the meaning of the partial derivative computed slope. Now, it doesn't have to be on x-axis, but needs to be parallel to x-axis, because right, it's not a comma 0. A comma 0 is on x-axis. A comma b is going to be moved, but it has to be parallel to x-axis. Rotate this picture 90 degrees, you have the same thing for y. So you have to now get used to in Calc 3, if you haven't yet, you have to use the fact that your x and y are both equally valid and powerful independent variables. I used to be x only, now it's x and y. So whatever you learn for x, it's the same exact idea for y, because now z is your independent variable. Okay, so now let's talk about mechanics. We talked about the, oh, by the way, if you take your linear algebra, depending on how deep you go, one more notation will arise, and that's dy. Dy and dx. So this type of notation. So if you see this in your linear algebra course, if you're taking linear algebra, please note that it's a partial derivative, okay? Partial derivatives will be the part of your first chapter of differential equations as well. So make sure you do that. And then also depending on the level to which you will be working with magnetism and electricity and magnetism in your physics, you might run into partial derivatives again. Obviously, higher coursework at your four-year school later in STEM will include partial derivatives as well. So it's not just let's pass Calc 3 exam and we're good, right? You're going to use this stuff later. Mechanics. So say that z is given as xy squared plus sine y. So this is some kind of a surface, right? You can go in your favorite graphing tool and, you know, plug this in, and you are going to get some kind of wavy surface because of sine y. Can't do it in that one, right? The graphing, because it's only 2D. Now, we want to find partial derivative in respect to x. We call that zx. We can also say partial of z, partial of x. Please put note in your notes. Wow, note in notes. That when you are looking for partial derivative in respect to x, your y is treated as a constant. Because you are, when you remember the picture, the y was constant along the way. For x-axis, y is always 0. If you move parallel 1 unit, then y is always 1, while x varies. So for partial derivative in respect to z, hold your call this one, called y constant. So what do we have? Well, if y is a constant, then that gets copied, and the derivative of x is 1. And then if y is constant, then sine of a y is 0 in a derivative. Right? If the whole thing is constant, the derivative of constant is 0. So the entire derivative, partial derivative in respect to x, is just y squared. Now this all changes for partial derivative in respect to y, which is partial z, partial y. Now x is a constant, and the derivative of y is 2y. So we have 2xy plus cosine y. So what are the stumbling blocks and things that you have to worry about? Try to immediately separate these procedures and techniques from your implicit differentiation from Calc 1, right, and chain rules, because they're not here.
Should that be a negative cosine chance?
No, the derivative of sine is cosine. Integral of sine is negative cosine, right? The derivative of sine is positive cosine, so it should be positive.
Oh, never mind.
Integral of cosine is negative sine. You are used to, from Calc 1, when you take derivative of y, follow that and write dy dx chain. None of that stuff here, right? X and y are both independent variables. They do not require any chain rule. And if you are doing the partial derivative in respect to the opposite variable, then they're constants. So they're either independent variable or a constant. They are never a function, right? Now we're going to do the chain rule next lecture as a chain rule, and we'll see what that brings to the table. But right now, your job is to say, oh, partial derivative of x, y is a constant. Partial derivative of y, x is a constant. And you take your derivatives accordingly. So, as I'm taking the derivative in respect to y, the derivative of y squared is 2y. There's no chain rule there, it's just 2y, because y is independent variable, as good as x, okay? So, I have 2y, this is a constant, and we know that we are supposed to copy the constant, right? So you copy the constant times the derivative of the variable part, which is 2y, so 2xy. And then here, y is the main variable, independent variable constant, so sine of y is just cosine of y. Again, no chain rule, no nothing, these are all independent variables. Z equals, this is a new example now, see you next week. Z equals, say, y cosine y minus x squared. So partial derivative in respect to x, so partial z, partial x, is equal to. Yes?
Is that going to be y cosine of y minus 2x?
Well, remember that y is a constant.
Oh,
Derivative of constant is?
0.
Nice. So, negative 2x. Good. That's that. So, the entire first term dies because the entire term is constant because there are no x's. The partial derivative here says x is the variable. X is the only variable we care about, and the first term did not have any x's. That means if it doesn't have a variable, then it's a constant, right? And the derivative of constant is 0. How about zy? Partial z, partial y. How about this? What do we do here?
Sine y minus y sine y.
How'd you get that? What did you do?
Well, multiplying y cosine y to get product rule.
Product rule, thank you. I'm waiting to hear that. Yes, it's a product rule. This is a basic calculus 1 question. You have y times cosine y. It's a basic product rule. So, copy the first times derivative of the second plus copy the second times derivative of the first, and then the x squared has no y's, therefore minus 0, it's all constant. Cosine y, there we go, is 0. So this over here is the product rule. Come on, Red. Thank you. Product rule. So you have to be careful that all of those basic calculus 1 rules are going to lurk within this. There is no separate product rule or quotient rule that you have to learn for partial derivatives. No, we are using Calc 1 product rule and Calc 1 quotient rule within here. The little bit challenging part is that you will be using Calc 1 chain rule, and Calc 3 has its own chain rules, plural. Rules, with S at the end. So yeah, we'll deal with that next. So, as I am simplifying this, right, zy is equal to, you always look if you can factor anything, because remember, we're going to do application for this, right? Eventually we're going to say equal to 0 to find critical points. We want min, max, and all that stuff that we did in Calc 1. So, if you can factor, factor. Well, we can't do anything here, so it's cosine y minus y sine y. And we are done. But next week, this would be the first step. We say equal to 0, solve for values, and then procedure for min, max. It's going to be a party. Right? Right. Good. So there they are, partial of z and partial of y. More examples. The more we have, the better we... one that is frequently floating about, 3e to the x squared plus y squared. Right? This is something that you should definitely see on one of your homework assignments or so on. I'm going to go fill my water. I'll be right in. Drunk this for you. Actually, I think this. If I go out of range, the elements will take that thing.
as a constant. So the derivative of x is 1. So 1 times a constant is just a constant.
Okay. Just the
Yeah, because the derivative of the constant is
Test. I keep working on this, and please check with your fellow neighbors. Compare. Probably so far, this might be the most important problem we do today. This one. Peak frequency. I already said that. So. Just realized it's been like 20 years since I wrote my Cyrillic alphabet. I want to do it. While you guys are enjoying this. Got it. Look at that. What's this? V, exactly. That's B. That's V. What's this? R. That's R.
minus 5, 6.
This is P. So, can you imagine learning this? This is your first grade, and then you move to the alphabet that it's exactly the same, like here, where this becomes P, and it was R last year for Cyrillic. This becomes B, and it was V. And then your homework assignments is you write, when you learn Serbian, you write one homework assignment in one, and then the next homework assignment in the other. Yeah, this is why our brains are wired and going like, wah, no, non-stop. In second grade, you poor thing, you have to do like third grade. You don't even know what your name is.
What's the snowflake?
Snowflake is J. And I told you there's no X. This is H. If I write the Latin, this symbol is not there. This is U. U, like you. U. So you will say, well, if you say cool, it's two O's. This is, and the entire world, the best system to have to speak and write and read, absolutely the best. No double letters, no spelling, nothing. The way you write it, the way you read it, sound by sound. So we don't teach spelling. Spelling doesn't exist as a concept in my language at all. Because the way you say it is the way you write it, the way you read it is the way you say it. Yeah. Absolutely no difference between the two. Yes? What happened? I can't hear you. Air conditioning over here, and you're just saying, ooh. All I heard is, ooh. All right, let's go and deal with this. So that was a little detour, right, to have some fun with foreign letters. Now you will recognize some of these are in advanced physics notation, right? You will recognize some of these symbols. there. Number 3 is z, by the way. Yeah, good luck with that.
Write your name.
With the marker. Later, let's have fun with this. So partial derivative. This problem is very important for 2 different reasons. Reason number 1 is exponential and very high frequency because it actually converts into polar later on and all of that stuff. The second reason is this particular type of function is symmetric. Symmetric functions are those that if you swap every x for y and every y for x, you get the same thing back. So a function x squared plus y squared is symmetric. Function x squared minus y squared is not symmetric, right? Because subtraction you can't swap. Now, we are going to learn now one of the very cool properties of symmetric functions that will save a lot of time for you as you are looking for various partial derivatives. For instance, what is the partial of z in respect to x? So that's partial z, partial x, and that's the, now, we know that the derivative of e is e. So this is going to be 3e to the x squared plus y, and then the calculus 1 chain rule kicks in, giving you 2x here. So the whole thing is 6x e to the x squared plus y squared. And that's it. Now, this is the power of symmetric functions. Partial derivative with respect to y, which is partial z, partial y, is equal to 6y e to the x squared plus y squared. See that? So that's the power of the symmetry in equations. This was a symmetric function. You have, so they pop up. You know that the function is symmetric if when you swap x with y, you get the same function. So you replace, for each x you put y, for each y you put x. And if the function is still the same, then that's a symmetric function. Immediately that means that when you take the partial derivatives, partial derivative in x and partial derivative in y will be the same as you swap all x's with y's. That's all I did. I just swapped x's for y's. We know that this will just turn, but we can turn it back, so it's okay. See? I just swapped that in. Now you can see that here, if you fill this step in, it will start off the same way, and then the chain rule will spit out to y, which is exactly that y that we get here. So the property of symmetric functions regarding partial derivatives is that, and they will talk about that in the book, right? Property is that if the function is symmetric, then the derivative you can quickly. Now, why is that important? It's important because when you're taking partial derivative of a sphere, for instance, right, and the sphere is x squared plus y squared plus z squared, right? You have to take partial of x, partial of y, partial of, right, z. That's work. But when you realize that the equation of a sphere is symmetric, you just find partial of x and just write the other ones instantly, right? You are cutting your work down to a half or a third of what you were supposed to do if you know this piece of information. Now, this will be very useful at the end of this chapter, this idea of symmetric functions, when we do min-max and Lagrange multipliers. So, we'll get there. Well, that's partial derivatives. Can we have a second partial derivative? And a third? And the fourth? And the fifth? Yes, we can. Right? We can. All I need to do is to take another derivative. How many can I take? As many as you want, right? As many as applications demand. How far did I see it in application? 4. I've seen 4 partial derivatives taken in one of the talks, seminars at NJT. So, right, can you take 16? Sure, go ahead, take 16. Yes? The what? Yes, because those are your independent variables. Simple.
Then when you take the partial derivative in the second partial derivative back, you have to take the partial derivative of with respect to
x, yeah.
And y with both of those two.
Well, you just do what you need. The answer is you have a lot. It branches out. So that's what I'm going to talk about now. So look at this. You have function z, which is function of xy, and you know that you can take partial x, which is partial f, partial z, whatever, f or z, same. Okay? Or you can go zy and get partial z, partial y. Now from here, you can find zxx, which would be the second derivative, like this. And from here, you can do zyy, which is the second derivative. Note how I crammed this in the corner? Why did I do that? Why am I cramming this in a corner? Because now with these derivatives we can do more than Calc 1. Calc 1 goes first derivative, second derivative, third, fourth, fifth. These ones have mixed derivatives. I can start here and get this guy. And that's called a mixed partial derivative. So, it's still a second derivative, but it's the second derivative where first is in x and second one is in y. On the other side, I find this guy. And then we have a theorem that they're the same. But so, you see immediately that if you are to go to the third derivative, now you have third derivative to be zxxx, zxxy, zxyx, zxyy, zyy, right? 8 combinations for the third derivative if you have 2 variables to start off. And you can have also as many variables to start off as you want, not just 2, x and y. Yeah. So you need to know exactly what you need. Otherwise, computing random derivatives is pointless, right? Especially that there are so many of them if you're going to the third or the fourth derivative. You have to know exactly what partial derivatives you need on which tier of the derivative. And to get there, you have to go and get all of those. So let's take a look at first a basic problem. So say z is given as x cubed y minus cosine xy. So this should be a good function to learn this. Partial x, also known as partial z, partial x. If I have this, it's 3x squared y minus plus, because the derivative of cosine is negative sign, y sine xy. So if x is a variable, y is a constant and jumps in front using the Calculus 1 chain rule. Are we all green on that? Cool. So this y jumps out because of the chain rule. Derivative of cosine is sine, negative, negative is positive, so that's all cool. Now I'm going into zxx, which is second derivative of z, right, dx squared. Cool, welcome back. And now we're taking another derivative in respect to x, so that's going to be 6xy plus, and now I have to take another derivative in respect to x. So that's going to push another y out, so we have y squared cosine xy. Ta-da! Right? However, in blue now, from here, I can also get zxy. And this is what it's known as the mixed partial derivative. Now, the notation for this one is this. Because we did this first, you read the derivatives this way, right? Because if you are to have a function here, you apply this first and then this one second. So you list them in reversed order, right? Always reversed order here and here. Because these are all about what's applied first, and because the stuff is here, clearly this gets applied first, which is the first derivative, and then you go with the y, which is the second tier, second derivative. So this is the notation. Please remember and put a note that they are reversed in these two notations. And I have to look back here, because now I'm doing the second derivative. Every second derivative is done off of the first derivative. So I have to go back and look at the first partial derivative and do the derivative of y from there. Now that involves the product rule, right? So we see that for this particular question, xx was easier to do than xy, because xy has a product rule limit. So we go back, derivative in respect to y, so that's just going to be 3x squared plus, and now we have to do the product rule. So copy the first, derivative of the second. No, we are taking the derivative with respect to y, so x is out. Okay? Plus copy the second, and derivative of the first. And there it is. So this is the mixed partial derivative that we have. Now note that these are all derivatives where you start with x. So you have partial x, partial xx, partial xy. You are going to have 3 now for y. Partial y, partial yy, partial yx. And a partial yx must have same answer as the blue one. Because partial xy, partial yx are the same. We have a theorem for that. I know I didn't teach it yet, but preemptively I can tell you what's going to happen. So now I'm going to ask you to compute z of y, looking at the function, and then zyy, and if you can, zyx. We're going to do the zyx, let's say orange. Okay, let's take it. I can't even speak anymore. All right, so partial derivative in respect to y will give us just x cubed here. And then minus partial derivative in respect to y, plus, will kick x out and have sine xy. So I can do the derivative of y. The y will go to 1, so only the constant x cubed survives. This is the same like, so this x cubed y is like observing 5y. And if you take the derivative of that, it just becomes 5, which is x cubed. So that's that. And now we don't need anything else anymore. We have our first derivative to get our two second derivatives. To find zyy, I take the derivative of x cubed. That's a constant now, so that's 0, it's gone. And this will give us another x out. So x squared cosine xy. It's not a product rule because there is only one y and we are taking the derivative in respect to y. So x and x is a constant. The chain rule, Calc1 chain rule, will kick another x out because this is as good as a sine 3y, let's say, right? You would kick 3 outside for the derivative. So we are done. That's zyy. It's just x squared cosine x, cosine xy. Now we get to the next part where we are supposed to take the derivative of zy in respect to x. That's the mixed one. Switching to orange. And whatever we get here, it better be identical to the blue line I had earlier for the partial xy. Because that's the theorem in mathematics, and we know there are no exceptions to the rule. So we do, again, we are looking all the way up there. The derivative is 3x squared plus, and now I have to do product rule here because I have x times function of x. So copy the first, derivative of the second in respect to x. So that's going to put y outside. Plus, copy the second derivative of the first. When you compare the blue and orange, they're identical. 3x squared, xy, yx, same thing. With a cosine xy plus sine xy. Now, I can't put, so I have to zoom out and show the entire problem. This is how many derivatives you will be taking in 12.8 just to set up the problem. Calculation is going to be after that. So we will need zx and zy to set them equal to 0 to find critical points. We will need xx, yy, and one of these two to solve the second derivative test, which will tell us whether the points we found, these critical points, are min, max, or saddle. So all of this that you're seeing now is just going to be a setup for the problem that is either next week or following week, which is 12.8 in our curriculum here. So please, as you are practicing derivatives, I understand that your homework in your book will say, find the first partial derivative. Just crank this every time. What we need is we need speed, right, to solve, because you really can't afford to sit on the exam if you want one, and compute this for 3 hours, because you don't have that time, right? It's 1 out of 10 problems. So it has to be quick. So keep practicing the entire thing every time you see these partial derivatives. Good. The theorem that says that mixed partial derivatives are the same is in the book somewhere. Theorem 12.4 on page 900. Equality of mixed partial derivatives. Assume that f is defined on an open interval d of R2 and that fxy and fyx are continuous throughout d, then they're the same. There you go. Assuming sufficient continuity, theorem can be extended to any level. That means that let's say fxxy is the same as fyxx, fxyx, any combination, right? So as long as you maintain the same number of x derivatives and y derivatives, no matter which order you put them in, the final answer will be the same when you're done with all of them. So we go and look into well, we can do another example from homework, and then let's take a look at one of the application problems, so it makes sense. We have time. I want to take a look at something with more than 2 variables. You can have as many as you want. Problems 45 through 54 all have multiple variables. And some of them are symmetric, so that's really cool. We can do 2 problems quick. 48 is going to be insanely quick. It says that the q of xyz is given as a tangent of xyz. This is a symmetric function. All I need to do is to find one partial derivative. The rest are just going to fly out. So qx, I'm looking for partial derivative in respect to x. All right, so if you recall the calculus 1 derivative for tangent, it shouldn't be an issue. What's the derivative of tangent? Beautiful, secant squared. Leave some space and write secant squared of xyz. Now, which 2 variables are constants? Y and z. That goes in front because of the calc 1 chain rule. So derivative of tangent is secant squared, and you just write secant squared xyz, and then go in front and put the constants out in front because that's the chain rule, calc 1. Now, because I know the symmetry, qy will immediately be xz secant squared xyz, and qz will be xy secant squared xyz. So when you have symmetry, you exploit that symmetry immediately. You exploit it very simply by saying, oh, derivative with respect to x, no x here. Well, derivative with respect to y, no y there. Put the other 2. And the derivative of z, put the other 2. And you just cloud the whole thing. More problems like that. I'm going to show you the textbook now, page 904. 45, symmetric. 47, symmetric. 48, symmetric. And that's it. No, problem 50, symmetric. Because if I swap the values, I get the same function, right?
It's basically like, for now, it's just trial and error. It's how it's symmetric.
It's not trial and error. You swap the values and you get the same function back. You see, if I rearrange this x, y, and z in any order, I'm getting the same function back. Note over here that if I rearrange these, I don't get the same function back.
Oh, okay.
Right? Because if I swap x and y, then I have 2x and a single y. And that's not enough.
So it's the same coefficient.
So rearranging these guys, giving back the same. Rearranging these guys, giving back the same. This one, no. This one, yes, yes, no. Right? Because the quotient between these guys. I can rearrange, swap y and u and v and get the same in this case.
So if it's like 2z tangent of x, y, z.
No. Because you ruined it, right? If you have x, z, y tangent x, y, z, then yes, right? So it's very picky. The rule is you shuffle the x, y, z's around and you get the same thing. Good. One more of these. How about 53? It's beautiful. We haven't done any quotient rule, and also has 4 variables. So function h, in terms of w, x, y, and z, is wz over xy. What happened? Partial of h in respect to x. All right. I just realized that I said something terrible. I said quotient rule. Please don't use quotient rule. You have single x, single y, single w, single z. This can be very easily written as wz xy to the minus 1, which is wz x to the minus 1, y to the minus 1. Please note that this is the only place where you have a variable. The rest is a constant. So immediately, wz over y is a constant, and I just need to take derivative of x to the minus 1, which is minus 1 over x to the minus 2, which is technically x squared in the bottom. So, negative and x squared, and we're done. So no need for quotient rule. We rewrite it. Now, partial derivative in y well, if you look, just x and a y, they're symmetric. So immediately the answer is negative wz. This is not fully symmetric. But if you just look at pairing between wz, it's symmetric, and pair xy is symmetric. What is the partial derivative in respect to w? Well, if w is the variable, the rest is the constant, so it's z over xy. And partial derivative in respect to z is going to be w xy. As I said, these are symmetric as pairs. So there's no need for quotient rule. I spoke too soon, right? I spoke too soon and got this. So we have symmetry, partial symmetry here, because if you swap these two, the function stays the same. If you swap these two, function stays the same. If you swap them this way, function is different. So if you notice, I mean, I'm hoping you're learning the symmetry because it really helps later on with the partial derivative, especially 12.8, 12.9, when the chapter. So one more time, symmetry means you swap two variables, function remains the same. So multiplication is commutative. So by swapping these two, I change nothing. And that's why the derivative partial of x and partial of y have the symmetry in the answer. This one is x squared, this one is y squared, right? If I swap again w and z, no issues, which is why the derivatives. Now you can see the derivatives between these guys are vastly different. So there is no symmetry this way, but there is symmetry that way, which is why these guys work the same and these guys don't work the same. So this is a very good example for you to get sense of the symmetry and practice and so on. Is it necessary? No, it's not necessary. By all means, it's not necessary to figure it out. But it's great help when you run into some of these problems that are going to be there later on. I wanted to talk about application problem. For whatever reason, thousands of people take chemistry because it's fun, and for whatever reason, or physics, and for whatever reason, there's one formula which is completely random that everyone remembers. It's completely random. That's the force. No, I'm not talking about that formula. So yeah, there is the formula, the velocity, distance, time, and F equals ma, which is the force. I'm actually talking about ideal gas law. I don't know why, but I see some of you shaking your heads already, right? That PV equals nRT, and now you're starting smiling. I don't know why, and also in my case, PV equals nRT. P is pressure, V is volume, T is temperature, and N and R are constants. So pressure, volume, temperature. And we call it ideal gas law, which means it doesn't really work for the air in the room or the tires, but it's close enough, so we can just use it. Cars, tires, maintenance, all of that kind of stuff. Don't you notice in the summer that there is a lot more debris on the highway than in the winter? Right? And I'm particularly talking about exploded truck tires. Why is it so? Well, we know that is why.
Because as it moves, the tires get hotter, the air expands.
Very good. Yes. Yes. So if you're not on top of your game as a driver and you just do whatever, now most of the cars are equipped with sensors to tell you something is wrong with the tire pressure, it's too low, too high, or so on. The debris shows you that we are not there where it's completely eradicated, right? Notice that pressure and volume are on one side and temperature is on the other. That means they grow together. So if the pressure and volume go up, temperature goes up, because this is constant. This is not there, okay? That's constant. So if pressure and volume together go up, the temperature goes up. Now, there's just a certain amount that the tire can expand, elasticity, right? it's rubber. So think about this. If you keep any of these constant, let's say pressure is constant, as the temperature grows, it's hot summer day, and you're on a road, there is friction between tire and the road, which is why you're able to drive. Try doing the same thing on the ice skating ring and see how well your car is going to work there. See, there is no friction between ice and a tire, which is why the car slides on the bridge, right? Bridge surfaces freeze before the rest of the road. You've seen those signs? Your tires don't work well on ice because there's no grip, there's no friction. Friction is heat. Experiment 101. You should do this in kindergarten. They do this, right? And you feel two surfaces rubbing against, right? If you take the eraser and use it on your jeans, you're also going to feel hot, right? So that's friction. Friction causes the heat. You can always warm up your hands like this in a winter, right? So heat is temperature. So hot outside, friction between tire and the road, you have excessive heat there. Much more than in the winter. And that means that the right-hand side has to go up. If pressure is constant, the volume has to go up. But it can't. Right? So what are we supposed to do with tires in summer? Take some air out. Your tires are rated for 36, 40, 50 psi, depending on what tires you have. You are supposed to maintain the proper pressure, right? Now on cars, there's not that much weight and that much pressure and so on. So generally those tires are more resilient. But when you have a truck fully loaded on the wrong pressure, yeah, those tires are going to explode. And you see them as you drive in the summer. Debris everywhere on 78, which is technically like snowboarding around them, right, going around. And it's very dangerous, right, to leave that stuff on the road. So these are the things that now we can see in calculus. So now we have a function which has these three as variables. Pressure changes, volume changes, temperature changes, and are constant. What Calculus 3 allows us to do is to measure the change of pressure in respect to temperature, the change of pressure in respect to volume, the change of volume in respect to temperature, right? Any combination, because we have partial derivatives. So now, if I go and I say Tp, right, Tp, this is partial derivative of temperature divided by the partial derivative of pressure. This measures change of temperature in respect to change in pressure. And you can come up with any one of these. And then you know how to take partial derivatives, so you can take that. And as engineers, guess what? You have to. Because you're designing this thing, right? Your company is responsible for lives of all of the people that bought your product. Right? Ultimately, you are as engineer. So you have to be able to compute these changes and know what are the levels that you have to advertise in. Put the caution, and then you are legally okay. Right? Then survival of the fittest kicks in, right? And let the people not pay attention and whatever. But your responsibility is to do the right on your end as engineers. Hashtag Florida again. Volume. in respect to t. This is the one that, right? And in respect to p. Those are the ones that make the tire explode. So this is change in volume over the change in temperature. Vp, change in volume over the change in pressure. And you can find any of these as soon as you flip things around. So what do I have? Let's calculate V of t. To calculate V of t, I better have V alone on the left-hand side. So P gets shipped to the other side. So volume is equal to nRT over P. And since I am taking the volume and the temperature to be variables, that means that the pressure becomes constant as well. So we have partial V, partial T is going to be nRP. So whatever the pressure is at that time. So you go and you pump 38 psi in your tire, and you have 38 over here, and an R constant that are known, plug those in, and you get the volume. Yes. The change, sorry, you get the change in volume. So that's by how much the volume will change. It's a positive number, how much it's going to change up. So the question is, can your tire expand that much, right, to accommodate for that change? If it can, it will explode. And those are the things that you as engineers are working on to make sure it's okay. So that's one of the applications that you can think about. Bye.